Hey, welcome back to Fat Mama Physics. In this video, we're going to do an example on atomic line spectra. So this is topic 7, and for our lesson purposes, this will be tagged along to 7.10 discrete energy levels in emission and absorption spectra. So let's begin. This is an IB style question, so very relevant for us. Let's begin. Explain how the wavelengths of an atomic line spectrum relate to atomic energy levels. So, it's an explain question, and I know how annoying explain questions can be and how many of you may dislike these type of questions. So, when I see, this is an approach. You don't have to use it, but one possible way to help you to fully get all the possible points in this question is what I would do is on the side of my page or on a scrap piece of paper, I know I need to make the relationship between the wavelengths of an atomic line spectrum. Okay, so this is the spectrum that you see, and you only see some specific lines, and you want to relate that to atomic energy levels. So this is the atomic energy levels you expect to see maybe for hydrogen. So notice so you want to make that link. So what I would do is on the side of my page, I would kind of build a flow chart for myself, so that when I'm actually writing this down on my sheet of paper here, I'm doing it in a logical, coherent manner, so that I don't miss a single step in which a point could be possibly awarded. So I'm going to move, I'm going to erase this over here, and I'm going to start up here, okay? So first of all, we're going to start with these wavelengths. So specific wavelengths, and you know what? If you're doing this one on the side of your page, you can just doodle on the side. You are not going to get deducted marks just by doing that. What the IB would mark is whatever you show here. So it really doesn't matter about that. So we know that we want to go from wavelength all the way to atomic energy levels. We know that atomic energy levels are discrete, and they're also finite, okay? Meaning that there's only specific jumps that the electrons can make, so that would correspond to only specific wavelengths on a line spectrum. So notice how when I'm thinking about this, I'm going from my final point and I'm working backwards. So now that I kind of have like a flow in my mind, when I want to explain it, I want to explain this in the forward direction. Usually that is the preferred method when you approach an IB question. You always want to go from point A to point B. Logically speaking, it's a little bit, you can run into troubles if you're trying to explain it in a backwards direction, because there's other things that could be involved. So for wavelengths of so how to approach this is that we know specific wavelengths correspond to specific energies of a photon. If the atomic line spectrum only has certain wavelengths that are being shown, it means there's only specific energies of photons emitted from a particular sample. This must correspond to the electrons dropping specific energy levels, dropping down specific energy levels to produce these photons. Okay, so that means I need specific energy level drops of electrons to produce these photons, and this must lead to the fact that in order for us to get specific photons of specific energy, there can only be discrete energy levels for which these electrons are able to drop, okay? This is not usually, usually we like to explain it in the direct manner, but if you want to think of it the other way to help you to help you think through this process, imagine that there aren't discrete energy levels. Imagine there are infinite amounts of energy levels. If there's infinite amount of energy levels, then the electrons can jump however they want, meaning that you're going to get absorption in all sorts of wavelengths possible. And since that's not the case, you don't have infinite energy levels, and you most definitely are not going to have a continuous you must have discrete energy levels for that to happen. Okay, so I write down my flow chart, my line of thinking, and then I can go ahead and write out exactly what I want in the space provided for me. When I write it in the space provided for me, I'm going to go from where I start off with, which is the wavelengths of the atomic line spectrum, all the way down to where I want to relate it to, which is atomic energy levels. And it's ideal if you actually use those words in your explanation to help the examiner know what you're talking about. So after I establish my flow chart, I convert that into words, explaining the thinking one step at a time. So going from wavelength to specific energy of a photon, specific wavelengths of photons either emitted or absorbed for either an emission or an absorption spectra of an atomic line spectra correspond to specific energy levels of these photons. And notice I try to use the words that are provided in the question itself. These specific energy levels of photons are produced when electrons drop from a higher energy level to a lower energy level, meaning that the difference in these energy levels correspond to the energy of that photon. And as well, and because it's whatever is correspond to the photon released by such electrons, and because only specific wavelengths of light are emitted or absorbed, that means the electrons must jump between specific energy levels that are discrete and of course finite in nature. So in the explanation, I try to include everything that is necessary, that's absolutely important to associate this the wavelength with the atomic energy levels. Okay, so I know that's it's always good to I know this is a bit of an overkill for this question, but I think for explain questions which are troublesome for a lot of students, I think that overkilling the question is better than kind of undershooting the question. So to guarantee you the 3 points, okay? So never miss any logical step in your reasoning. Okay, so that's that. Here, talking about calculations, stuff that we are probably more comfortable doing. The wavelengths in the line spectrum of atomic hydrogen are these numbers. A photon of wavelength of this has an energy of this one. Deduce that a photon of wavelength this has an energy of 2.54 electron volts. So here we just have to do a bit of calculation using the Planck-Einstein relationship. So whenever you have a question where you are trying to show that this A gives you B, you always want to go from A to B, never from B to A. It's always better to move forward in your logical step thinking as opposed to moving backwards. Of course, when you are, say, playing around with numbers, or if you're absolutely not sure what to do, feel free to go from B to A in your own workings. But when you're showing your work, always show going from A to B. So here I'm going to show how this wavelength corresponds to this energy. So I'm going to pretend that I don't even know this right now, okay? So to find the energy, we know that according to the Planck-Einstein relationship, this is Planck's constant times speed of light divided by the wavelength, okay? And the Planck's constant from your data booklet 6.63 times 10 to the power of negative 34 joule seconds times the speed of light 3 times 10 to the power of 8 meters per second. All of that divided by the wavelength 486 times 10 to the power of negative 7 meters. Actually, that's negative 9. Okay, so that's going to give us, this is 409 times 10 to the power of negative 19 joules. And to give us electron volts, we're going to divide this by 1.6 times 10 to the power of negative 19 electron volts per joule. And that's going to give us 2.557 electron volts, which is roughly equal to 2.5. And you know what? I'm just going to write electron volts here at just 2.5 instead of 2.54 because it's not actually 2.54. And it's not the end of the world. You use all the numbers in your data booklet. The reason is probably having to do with these constants. For example, the speed of light is it's not actually 3 times 10 to the power of 8, it's 2.997, so it's very close to 3, and this elementary charge is 1.602, I believe. So all of these little minor imperfections will give us a number that may deviate from what's in the key or whatnot, and that's okay. You show your work, this is what you know, and you should not get penalized for not getting exactly that number, okay? Okay, so NS1 mark. The diagram below shows some of the energy levels of atomic hydrogen. On the diagram above, draw arrows to represent the electron transitions that produce these two wavelengths. Okay, so the two wavelengths we're talking about is 656 nanometers. And this corresponds to energy transition of 1.88 electron volts. The other one is the one we just calculated, 486 nanometers, which is 2.54 electron volts. So what we want to do is we have to be very careful. We need to draw arrows representing the electron transitions that produce these two wavelengths. And it looks like that photons are produced in this case. So this means that we're talking about emission spectra. Emission means that the electron is going to drop to a lower energy level. So that's something we just have to be careful of in a question, is whether or not we're talking about electrons moving up or transitioning to a higher energy state or lower energy state. I mean, they're both going to correspond to the same energy difference, but whether or not we're talking about a photon that's emitted versus photon is absorbed, that is the importance here. Since it is produced, we have to do that, the electron must drop down the energy level associated. So to get the first one, 1.8, whoopsies, to get 1.88, we're going to look at energy transition that corresponds to that, and it looks like it's going to be 1.51 to 3.4. So if you put that in your calculator to find the difference, I get 1.89 exactly. So that's going to be our first drop here. So that's the first one, okay, that's an arrow. And the second one corresponds to an energy difference of 2.54. So it doesn't look like this ground state is going to be involved, because that's a huge jump. That's a really large amount of energy. So 2.54 will definitely not be anywhere from the top to here, because that's not enough. So we're probably not dropping to the third level. We are likely dropping to the second level, which is 3.40. So if it's not 1.51, let's try 0.85. If I take 3.4 minus 0.85, I get 2.55, which is pretty similar to this 486 nanometer. So that's exactly what that should be what I'm going to get here, is that drop from the fourth energy level to the second energy level, producing this photon here with a wavelength of 486 nanometers. Okay, so that's here are the particular transitions. I double check, it is 2 marks, so I probably don't have to do too much more here other than just labeling the transitions. Okay, all right, so there we go. This is looking at line spectra for an IB question. So hopefully you learned a little bit from this question. I hope you try your best with your explain questions. Good luck. Thank you for watching. Fat Mama Physics signing out.